The main concern here is that the length of the geometry or even the all dimensions should be correctly modeled in the case. So what I did is that I searched for the Boeing 747-400 length, and it comes out to be 71 meters. And I want to check the same length for this model. And here the length is, if I go to the pull command, and then I can use a measure tool and just select the 1 point on the fuselage on the upstream side and the 1 point on the downstream side. This can be anywhere. And this is around 169.8569. So if I want to convert this to the 70 meters, so I will be dividing the 169.8568 by the 2.39. So this will be 71 millimeters. And if I multiply by the thousands, I will get a 71,000 millimeter, which is equal to 71 meters. So in simple words, if I divide the 1000 by the 2.39, I would get the 418.41. And if I multiply the dimension of this aircraft, which is in our case, so this is the 169.8568, I multiply by 418.41, I would be getting around 71 meters. So it means that the factor we are going to use for the when you import the mesh into Fluent, so I will be multiplying by the 418.4. So I will be multiplying with the 418.41. This will be our scaling factor for all three dimensions in X, Y, and Z. Okay, this is a small demonstration that how you can scale the geometry in the Fluent. And now open the Fluent setup. And before that, you should be updating the mesh as well. So right click here. And you can also close the geometry. So before you start the Fluent part, you can simply right click here and update on the mesh. So the update has two things to do. One thing is that if the mesh is not computed, this will compute the mesh from the sizing set on the different faces or the volume, and then it will translate the mesh to the solver. So that can be any solver. This can be the CFX or maybe a Fluent. And the mesh is updated. Next thing is to double click on setup to open the Fluent. And I will use the 4 processors because I have the 4 cores in my CPU. And with this much mesh, like a 3.5 or 3.2 million cells, you should be going with a more cores. Maybe you can go with the 8 or maybe 16 cores. So more the cores, and it will give you the more speed in terms of the solution. But my limitations right now are that I cannot go beyond the 4 cores. This is the maximum size I have right now with my CPU. Okay, so we discussed about the scaling of the mesh so that we can make the Boeing length to the 71 meters as given on the internet. Just read the mesh file. Okay, now you can first display this mesh with the cells on the mesh as well. And let's say if I hide the boundary condition from this, is the boundary is basically a combination of 3 surfaces. And now you can clearly see the mesh. In the ANSYS meshing, it is very hard to see the mesh properly. but here this can be very much visible. And the last thing I just observed that we didn't take care of this edge over here. That's why this edge is diffused into the main geometry. And this was very, very small feature. So you have to take care for that feature as well. So you can go back to the meshing and define some proper size as I described in the video on the meshing. On the other faces, you can see the size is defined very properly. And including this very small feature here, and these engine naceless are the pylons. And also you can see that we have the very good quality prism layers, and number of layers right now are the 10. So first thing which we should be going to do is that is a scaling. So I will specify these ones by myself, and I will be using the 418.41 in all directions. And click on scale. And you can see that the dimensions are also changed according to that value. So only difference you can see here is that everything else is same. The only thing which we can see is that the size is larger for the geometry as well as for the domain and as well as for the mesh. So everything are scaled up with the same factor. Okay, you can also check the quality. And the orthogonal quality should be same as we have seen in the ancestral meshing, that is a 0.05. And aspect ratio, maximum aspect ratio is 100, which is also okay. Okay, so by default, we have the SST turbulence model, and on the boundary conditions, I will change the inlet condition to the pressure fault field. And I will define the Mach number as the 0.6. And since all the flow will be in the y direction, that's why I will choose the positive y-axis. So y component is the +1 and other two components are the 0. And the Mach number is the 0.6. And also for the material properties, I will be using the compressible flow. That's why I will choose the density to be the ideal gas, or maybe you can use the Bosniak approach, but I will use right now the ideal gas. And for the viscosity, you can use the Sutherland law. And but you have to take care of these all parameters. Okay. So now click on change create. So for the better modeling of these properties, you have to take care of these things, and you should be consulting any compressible flow, or maybe you should go with some thermodynamics books, and from there you can get this data very easily. Okay, so we define this thing to be there, and this will automatically turn on the energy equation, because as soon as we turn on the ideal gas, so this will turn on the energy equation. And also you should be making the solid type to be on the density base, because now density is a variable, so we should be running the solid as a density based. So we change the few things here. One is the material properties. Second is that we change the inlet condition from velocity inlet to the pressure far field. And then we change the solid type to density based, because now density is a function of the temperature. And also you should be taking care of this boundary and make it as a slip condition. And therefore I will define this as a specified shear with a 0 shear stress and apply. Okay, you can also define this boundary to be symmetric condition, and symmetric condition or 0 slip are the exactly same, that they will allow the flow to be flowing there without any development of the boundary layer. So with a 0 shear means that will be no boundary development on the surface of that boundary, and the velocity will not be 0. And also confirm the aircraft, this should be the wall condition, this outlet should be a pressure outlet, this symmetry should be a symmetry. Now in the methods, you can see this is the scheme right now. in the controls, you can put the current number to be initially to be the 0.1, and for report definitions, you can calculate the, for example, the drag coefficient or lift coefficient. And as far as the drag coefficient and lift coefficient are concerned, so you should be putting the proper values for the reference areas and the reference chord length. Okay, you can see that I have downloaded this document AR0444 PDF. And here we have all the data here. And I will use these calculators, online calculators, first for the area. And the wing reference area is the 5650. And this is the 524.9 to 0.9022. And therefore, I will go to the results and from here reference area and put it over here. And also I will be computing the reference values from inlet. So I would get some values from here, which are like the density and other things. Okay, the next thing is that to get the reference length. So the reference length is going to be because the mean error chord is equal to the mean error chord is equal to 327. So put this value 327.78. So this is 99.9 meters. So this is the wing reference area and the wing. Okay, this is inches. So I should be using the inches to meter. I was thinking that how is possible that the aircraft length is 71 meters and we are getting the chord length to be equal to 99.99. So it was not possible. So it should be inches, 327.78. So this is equal to the 8.3256 meters. And again in the length, I'm going to put this value. Okay, so this is defined. And also should initialize from the hybrid initialization. Okay, so we have initialized the solution. Next thing is to plot the report definitions. And here I will use the force report, drag, and then lift. So first put the name as the drag coefficient. And that would be on the aircraft. And I will be dealing with the drag coefficient. And direction is the y-axis, 0. And print to console. And definitely there's some angle of attack when the aircraft are moving in the air, but right now we are going with straight flow, that is with angle of attack is equal to 0. And in a similar way, you can define the lift coefficient. Again, the force, lift, and this is going to be the lift coefficient. And again, axis, this time the axis should be now along the z direction, because the normal to the flow, that is the upward direction, is z direction. So I will define the lift coefficient direction for the vector would be equal to the z is equal to 1, x0, and the y0. Again, the same thing, report file, report plot, and print to console, and click on OK. And now this is very important here, that when you click on run calculation, I will be using the solution steering. And what I would be using here is that I would be clicking on the more settings. And you can see the initial one we defined was the 0.1. So I would put the initial as the 0.1, and maximum I would set the current number to be equal to 50. So after the 100 iterations, this will start to increase the current number, and then the update interval for the current number is 20. So depending on solution acceleration, if solution is converging at the faster pace, means it's accelerating, so the current number will be increasing, and if the solution is diverging, this will be reducing the current number. So depending on solution convergence speed, if it is going with the downward trend for the regulars, this will increase the current number. And if this is diverging, means that the trend is going upward, this will increase the Coran number. Okay, and then now I will just simply click on the calculate. And by default number of iterations are 1000. So it will create the multi-grid levels like the 5 levels. So I will now wait for the solution to converge, and then I will discuss about the different plots like the vector plot and contour plots like the pressure, Mach number, and path lines. And then finally we will go for the drag coefficient and the lift coefficient. Here the solution has been stopped because the solution has achieved the convergence criteria. And now from the zero monitors, put some more zeros here, and then click on OK and start the solution again, so that we can run the case for the more iterations, so that although CD plot is now straight line, I'm just waiting for the CL plot to get a straight line. But if it continue to fluctuate around some mean value, then I will stop there and I will analyze the result. As you can see that the CL graph or the coefficient lift graph is fluctuating around some value, and so it shows that this will not converge to a straight or single line. However, the drag coefficient is almost a straight line, although you can see very small wiggles in the line there. But this is what we get right now for this case here. And this also happens because it's not possible to always have a straight flow or steady state flows. There may be some areas where we are having the separation, and the separation is moving with the distance in the time. So if you want to run some true simulations for this case, maybe at a higher angle of attack, in that case you have to run this case as a transient case, and you have to define time step and then get a data and average data over the number of time steps. But for this purpose, for this course, this solution is okay. And now I'll stop here. And also you can notice here that the Coran number increased from the 0.1 to the 50 within the, I think that within the 400 or 500 iterations. And the last 200, 300 iterations, they run with the constant value of the Coran number. So this is the result plot, this is the drag coefficient plot, and this one is the lift coefficient plot. And this is a contour plot for the Mach number, because the inlet Mach number we defined was the 0.6. And if I display the contour plots on the aircraft, and how I made this full body. So for that you have to go to view command and click on views. If you uncheck this and apply, this will be a single body again. And if you select the symmetry condition and apply, so this will make the full plane. And now if I see, this is not a exact geometry of the Boeing 737, and not the wings as well. The wings are straight bodies, straight rectangular wing, but for the actual wing we have some aerofoil shapes here. Okay, but I will be drawing the CP plot on this wing here. So for that I am going to use from results menu, I will use the create and isoclip, or maybe isosurface. Okay, I will choose the aircraft body, and then I will choose the x-axis as my meshing parameter. And based on this, I'm going to make one curve here just on the geometry of the aircraft, and that can be along the wing. Okay, let's say we draw the CP plot over here. So even this is true for the actual aircraft. If you get the proper geometry of this model, then this is again this is a procedure. Okay, so we have this curve here, and now I will use XY plot. And because the flow is along the y direction, so therefore I will put the plot direction as the y1. And I'm going to plot the CP, the pressure coefficient, where this should be on the x-coordinate 6. And click on the save plot. So this is the pressure coefficient plot. This is a zero angle of attack. Even if you go with some symmetric aerofoils, you would get the similar type of the results. But if you go with some high angle of attack, then maybe you can get the different results. Okay, now if I draw the vector plots on the symmetry plane, and at the same time I want to display the geometry of aircraft. So without any mesh over the aircraft, and simply draw the vectors on the symmetry plane. Just change the size from the 1 to the 5 scale. But as you go near to the geometry, so you have to reduce the size here. 0.5. So you can see that because of we applied the 10 layers, so we can clearly see the development of the boundary layer on the geometry of the aircraft. Okay, if I make another plane, that plane is this time this plane will be the complete plane in the whole volume, not just on the geometry of graph. This will be a line. So I will make a plane that will be a plane inside the whole volume. And this time I will not choose any geometrical part, any surface from here. And again I will play with the x coordinate. 1 minute. Okay, so this is the mesh, and click on compute and just move it slightly in this way. Okay, now get this plane and draw the vector plot. So we have these everything these which we made just now are saved here, are stored here. You can double click here and you can just change the plane. Also draw the mesh of the CAD model of the aircraft. And now this is the plot of the vectors on the geometry of the aircraft, but just on the wing. And you can see that we have this separation zone. And there's some reverse flow also on the rear side of this wing with this cylindrical shape body. So this will serve a purpose for keeping the engine. So in the actual case, this is the pylon with nacelles where we can put the engine. But right now, this is just a cylindrical body to demonstrate that we have something like that. Okay, now the last thing is that the forces. So I'm going to first, this is in the Z direction, this will be a lift force. And we are getting the negative force. And for drag force, we would put the y is equal to 1 and other two dimensions as the 0, 0. And the drag coefficient is 0.042. The one thing I want to mention here that in the reference values, the area should be half. So it means that because the model is half, so area should be the half here. If I divide by the 2, so I would get this area, 262.45. However, the chord length, because its chord length will be same, that is the same wing is here. So the chord length will be remain same. That's a mean aerodynamic chord. This will remain same, but the area will be half because the aircraft is now half. And now check the drag coefficient and the lift coefficient. So the drag coefficient is increased from the 0.04 to the 0.08. Okay, now, but if you apply the same technique which I taught in this course, you can get the accurate results for even for the actual case of the Boeing 747-400 model. Okay, this is about the whole thing that you can learn the quick CFD on the very complicated model with making the geometry, domain, and the high quality mesh with the prisms layer with the refinement region in the wake, and also refined mesh on the different parts of the aircraft, and the running simulation as a compressible flow with the inlet Mach number condition. And also we determine the reference conditions, then we ran the case. And also I taught you that how you can accelerate the solution using the solution steering. And finally we post process the results of the different things over here. So I hope this course will help you in learning the CFD very quickly, and within the 2 hours, I think you should be able to run now any simulation on your own. So, and if you have any questions, please do leave in the question and answer session section, and also if you have the any feedback on the course, please leave in the course feedback part. Thank you for watching this course.